Alright, so welcome back to the second part of the Thevenin video. In the first video, or the first part, we discussed the concept of output impedance. And really what that means is the difference between a real and an ideal voltage source. An ideal voltage source will maintain V volts, whatever its voltage rating is, no matter what is plugged into it. It'll always just force that potential between those 2 points. We could short those two together. We should get infinite current for 0 ohms. Something has to give. So what gives is that there's no such thing as a perfectly ideal voltage source, but there's a real voltage source that has an ideal voltage source with a resistor in series with it. Okay? That's a model for what a real voltage source does. Thevenin's theorem told us that if we had any complicated nest of linear circuit elements, I can look at between 2 points here, 2 terminals, say the blue and the red point on this circuit, and whatever goes in between those 2 terminals, whatever load is put there, we can put as an abstract load, and the action of the rest of the circuit on this load is equivalent to a real voltage source, namely a V-Thevenin, or ideal voltage, in series with a output impedance, R-Thevenin. And this is a very neat theorem in electronics that we can use quite a bit to understand how things function, right? So everything is a voltage divider. We plug in a load, and we've just formed a voltage divider between the internal resistance of the source and the thing we're plugging in. So now what we're going to talk about is how do we actually get V-Thevenin and R-Thevenin? And in the final video, we'll work through an example for an example circuit. So there's a few approaches we can use. They rely on linearity, and we'll go through them. So we need to get, let's just say, we need to find V-Thevenin and R-Thevenin. So let's look at a few limiting cases. So let's try to find out how we're going to find V-Thevenin. V-Thevenin, we're going to ask, what happens if we connect an infinite resistance load here? What if RL goes to infinity? And that really just means an open circuit. All right, here's the easiest way to make a infinite resistance on this wire, snip. You just chop the circuit, you open it, and no current can flow. We'll call this this green one here RL. Running out of ink here. RL. So RL goes to infinity. Well, our circuit is quite simple in this case. In this case, we have V-Thevenin in series with R-Thevenin, and what is the voltage dropped across R-Thevenin here? Well, from Ohm's law, it's I times R. So what is I? What is the current? 0. There's no current in here. So I have the same potential everywhere, even through this resistor on this side, anywhere along this line. Say if this is 0 volts, this is going to be V-Thevenin volts. So this is equivalent, remember, to this complicated mess of resistors here. So if I open the circuit and calculate, I calculate the voltage. So I'm going to open the circuit, calculate the voltage from A to B in this circuit. I get V-Thevenin. Open circuit voltage. I'm going to open the circuit, remove the load, and calculate V-Thevenin is equal to VAB, the voltage drop between these 2 points in your actual circuit. That's going to be V-Thevenin. Remember, V-Thevenin and R-Thevenin are independent of whatever we plug in here. So if we plug in infinity, we open the circuit, the V-Thevenin is going to be what it is. Now if I plug in a 2K resistor here, more current is going to flow, but V-Thevenin does not change. It's independent of this stuff here. So this is a way to isolate, neglect R-Thevenin and isolate only the effect of V-Thevenin. And once we've done that, we've performed this calculation, we'll go through an example next lecture, next video, then we know V-Thevenin forever. We know it for all possible loads. So this is step option 1 in our cookbook. What's option 2? Well, another thing we can do is we can exploit linearity. Remember what linearity says. It says that if I scale up the voltage sources by the same factor, a factor of 2, all the currents are going to double. If I scale the voltage sources down, similarly, by the same amount. So we can divide every voltage source, whatever it is, by 2, and 2, and 2 again, 2 to the 50, right? We can scale them down to 0. If I scale all the voltages down by the same amount all the way down to 0, I've effectively replaced this voltage with a 0 volt battery. What's a 0 volt battery? Remember, this is the ideal voltage source here, so it maintains a fixed potential of difference of 0 volts across it. It maintains the same potential. That's a lot of words to describe a wire, an equipotential surface. So if I scale down the voltages, scale all voltages down to 0, all voltages down to 0, in other words, I replace the batteries, all batteries, with wires. Batteries with wires. What does my circuit look like? I have a V-Thevenin, and I have R-Thevenin, but now I've replaced that with a wire. I've scaled everything down to 0, and I want to look at the voltage, or rather the resistance, between these 2 points. Whatever resistance I measure, I've removed the load and I've scaled all the voltage sources down to 0. Remember, this thing is equivalent. What I've gotten is just R-Thevenin. So I scale all the voltages down to 0. I replace all the batteries in my original circuit with wires, and I just measure the resistance, or I note the resistance between the 2 points and measure resistance. We calculate R from A to B, the resistance between node A here and node B. And that is equal to R-Thevenin. If I do that, I've measured my R-Thevenin. This is a good way to calculate V-Thevenin. There's at last one final way that we can calculate either V-Thevenin or R-Thevenin. So step 3, or 2B I would call it, is do either 1 or 2, 2A, to get V-Thevenin or R-Thevenin. And then note the following simplification. What happens if I short circuit these wires here? Let's replace the load with 0 ohms. Well, the voltage drop naturally across that circuit here. Remember, I'm just going to replace this thing with a wire, not a liar. And the equivalent voltage and resistance here is what I'm trying to figure out. What is the current here? The current that I measure in my wire is V-Thevenin over R-Thevenin. So what I do is we'll call this part 3, or option 3. We're going to replace RL with a wire, 0 ohms, i.e. a wire, and calculate current, or measure current, depending if you're doing it experimentally or not. Calculate current, and that is equal to V-Thevenin over R-Thevenin. Okay? So, say I know V-Thevenin, I can calculate my current and use that to get R-Thevenin. Maybe it was really easy for me to calculate R-Thevenin. V-Thevenin was a disaster, so I calculated R-Thevenin with option 2, and then I replaced it with a wire and found that was a much easier current calculation. So then I can use that to get V-Thevenin. All right? And this is finding V-Thevenin and R-Thevenin. You can do it by shorting out the load and then measuring the current. That is equal to the ratio of V-Thevenin over R-Thevenin. You can replace the load with an infinite ohm resistor and measure the voltage between them. That's going to give you V-Thevenin. Or, finally, you have a third option. 3 options to find 2 things, so you have a bit of leeway. scale all the voltages down to 0 and exploit linearity to note that the circuits are going to be unchanged, and in other words, replace all the voltage or the batteries with wires and calculate the Thevenin resistance in that case, because your circuit is simply this then. Okay, that is how to calculate V-Thevenin and R-Thevenin. What if we just had a circuit board in front of us? If we just had a circuit board in front of us, our situation might be a bit easier. We have this circuit, say, and we want to determine experimentally the Thevenin equivalent voltage and resistance. Let's do it. So experimentally, we can say plug in several different resistance values. We'll put in R1 here. R1. What do we get? And we measure V out. We measure the voltage. V1 we'll call it. Well, V1 is equal to R1 over R-Thevenin plus R1 times V-Thevenin. That's an equation we get. One equation, two unknowns. Looks like my red is on its last legs of ink or powder here. I can plug in a different resistor now. We'll plug in R2. We'll plug in R2, and we're going to measure a different voltage across that different resistance. And we can measure V2 is equal to R2 over R-Thevenin plus R2 times V-Thevenin. So already we have two equations and two unknowns, and we can solve for V-Thevenin and R-Thevenin algebraically from there. We can actually do a bunch of measurements. We can put a potentiometer here and measure a bunch of values and linearize this equation and do a fit to really accurately get the parameters V-Thevenin and R-Thevenin. Okay, so that's how you find V-Thevenin and R-Thevenin. An example would help a lot here. This is like a lot of pie in the sky concepts. So in the third and final video, we'll do an example of finding the Thevenin equivalent circuit of some circuit. All right, see you then.